is biological systems for purifying water as one of the many attributes of wetlands in as a habitat. Okay, so you'll probably see Dr. Clark, our professor from Bulgaria, speak to this with a different slide. And knowing that his lecture's coming up and we're layering detail, I'll speak somewhat briefly in this one just to capture in this graphic, and if you do Google Images, you'll see the same information portrayed in many different artistic concepts, hydrologic cycle, but the concept, of course, is the same, which is the whole system starts with evaporation and forms different kinds of clouds. One of the things that I love as a naturalist that stays with me everywhere I go from the training I got from my major professor is understanding and having a curiosity about what I see. And clouds are a really good example. Different clouds reflect the height in the atmosphere, the wind levels, different thermal gradients that influence how high they are. And then there are cloud circumstances that carry water in a way that is just before delivery. In fact, natural ecosystems, I touched upon this in speaking quickly about desertification. I'll talk a little bit more in detail about how natural systems create their own weather. They shape the clouds over their head and start convection processes that lift water to where it's colder, cause condensation, and precipitate and fall down as rain, or in some places snow. So here we have evaporation from both marine systems and freshwater systems. Lakes evaporate, human impoundments for water evaporate, and it's a real problem in arid areas that you impound water. The advantage is storage, but if it's particularly in a desert landscape, one of the losses you're creating that wouldn't otherwise happen is evaporation, meaning that that water is not available downstream for agriculture. And then transpiration is interesting. I don't know if you've had much botany, but a plant is basically a bunch of drinking straws that bring water out of the soil. We're going to talk about how water sits in the soil and the way plants can pull it out and then transpire it through small apertures in their leaves called stomates or stomata and carry it to the atmosphere. Of course, I think that's the very best way that water can leave an ecosystem because plants trap carbon as biomass. And plants have many benefits, but looking on the global scale, if it's a plant that's going to be there for a couple of 100 years, and then when it decomposes into very durable, sometimes called recalcitrant organic matter, that's carbon sequestration against global warming. So we have all these ways that water's moving into the atmosphere and forming clouds, which is a kind of interim condensation, and then when the condensation gets great enough in drops that are, that are under gravity going to move down as rain or snow, this precipitation is entering into our terrestrial ecosystem. So we're almost to the end of the hydrologic cycle, but the last part of it is the most interesting part because as it moves through these terrestrial systems, including under the terrestrial systems, that's where all the cool stuff happens. That's where the ecology happens. The biology happens at small scale, but of keenest interest to me as an ecologist is what's happening with all the plants and animals. So water that hits the land can move by as runoff. And that's where pollution is mostly transported. On Thursday, you're going to hear all about oil spill. Gravity moves very slowly. In fact, the fastest aquifers might move, I don't know, 100 feet a month or something, except for the occasional ones that you see, subsurface systems, and it's kind of marginal if we even call them aquifers or underground rivers, are in like the Indiana Jones movies where you go in these caves and they, ride these boats through caves with fast flowing water. And just like you have those big caves that are interesting enough for Indiana Jones movies, there are similar very small caves, but still have fast-moving water. One of the interesting experiences I had was cleaning up a really nasty site, toxic site in the United States. And we had some of those through a special type of topography, which is fractured limestone, called a karst topography. And we tested the rate of water movement by putting in a dye, a persistent dye, but not bad for the environment. And then we had wells downstream and saw how very fast the water got from where we put it in to the well, and it was moving like 3 or 4 miles an hour, as fast as, kind of a meandering stream, not as fast as a river, the middle of a river, but still, that was an exciting experiment to find out that. Okay, so any questions about this? As I said, we're going to drill down a little bit. And the time frame is this is a good day for me to just give a lecture. The whole concept right here is that you can ask me questions. It's kind of as an after the fact, and also our global people and the other classes can ask me questions. They will get to meet me online. You'll be in the room. There's going to be really cool video Skyping with them right here and the camera right there. And they will ask me questions, perhaps, about this lecture. Okay, so now we'll talk a little bit about pollution, in this case, surface water pollution. And this is just the basics, and we won't go too far beyond the basics in this class because we're covering all of water. In this course, we're covering all of water, from the literature to agriculture and policy. But we're also going to cover everything to some degree, and this is some of the most important information about pollution, and that is that we divide pollution into 2 categories. Surface pollution. We have point source runoff, and point source runoff is a discharge, such as you see here from a factory or a sewage treatment plant, which means that it's coming out of a particular, we say outfall, a pipe, as a concentrated source of toxicity, or speaking more generally, environmentally damaging chemicals or nutrients, like the excess nutrient created by removing sewage, the water from sewage. And so that's the form of pollution that was regulated for most of history in the United States, because it's pretty easy to regulate this. You can make this factory agree to reduce their discharge to a given level, and then you can monitor it. You go out and you sample right there, and if they violate that level, they discharge 200 parts per million of lead per day, or instead of 100 as as an accumulation over time. Then they violated their permit. They have to pay a fine and also prove that they're installing some equipment or changing their operations procedures so it doesn't happen again. It used to be, we had an interesting problem as far as policy goes, and as developing countries like Nigeria begin to regulate they need to think about this in advance. You calculate how much might be allowable to discharge, just kind of a general sense of the water quality you want to protect, but then more and more facilities as the city grows come online and they discharge, and they're all operating with an agreed upon limit, but more and more facilities with the same limit. It's going to create an accumulating problem that's worse. So one of the things they've done, a different regulatory paradigm, is instead of just discharging, monitoring and controlling these discharges based on the type, for instance, stormwater drainage systems, or even pulled off rooftops. That bioswale that I showed you, I talked about that. That's an example of a new paradigm for water management in the city that as we deploy more and more of, we solve this problem, even though there's not kind of a downstream regulatory scheme. Okay, so we're going down in scale to the very small level. We're going to look at what happens to water that infiltrates in a bit, where you can see that the water is fully, it saturates. Plants, do I need to take a break here? You having a problem with the equipment? Okay. Plants, except for maybe wetland species like cattails that we've worked with, they can't pull that water out. Their roots just lack whatever the mechanics are, the adaptation. There's a fancy word for it. It's good that I know it as a PhD ecologist, called a phreatophyte. I think my major professor was filling me up with what I call six-figure letters, so you sound like an expert, or terms when you're a consultant. You say, well, that system of phreatophytes is a good source of water removal, but pretty esoteric term. Let's go back to the difference here. This is the unsaturated zone. The water is stored around the edges of the particles, but during normal conditions, except right after it's rained, but after gravity's had a chance to drain it, the interstitial spaces are mostly water. The water stored on the edges of the particles are what plants take up because they can pull it away from those surfaces. And then as you have periods of drought, that means that very little water is stored in those interstitial spaces, so plants start to wilt because they don't have any water to take up. And in our climate, where we get a lot of rain in 3 months and then none for 9 months, we go through a long period of time when not only do plants wilt, they go dormant or die. So gravity works here. There's a little zone called a capillary fringe that kind of stores water in a, shall we say, an intermediate condition. There's a lot to be said about capillary fringes. I may talk about it more when we talk about pollution because it's important for that. But for the moment, I'm just going to say this plays kind of an intermediary role between the unsaturated zone and the saturated zone. And the saturated zone is where the water fully occupies the interstitial spaces between the soil particles. That's an aquifer. Now there are many different kinds of aquifers, but the saturated zone is an example of one. And the scale is such that if this were slightly tilted, or there was an area where it was tilted upstream and creates pressure, I should say really upslope, and creates pressure, this aquifer is going to flow. And all aquifers move, driven by gravity, albeit, as I said, at a very slow pace. Okay, so now we're going to talk about the different kinds of aquifers. I find this very interesting. I'm going to first talk about the water table and unconfined aquifers. Okay, an unconfined aquifer is water that does not have anything that pressurizes it on the up above it. So this is called the water table. Because it's not confined, it's not pressurized. If you were to sink a well there, the water wouldn't come out of its own pressure because there is no real pressure here, not enough. So you have to pump the water out. They would have done a better job moving that artesian well. Let's make sure it refers to this one and not this one. So the water is in a well, stays there up to the water table, and from there has to be pumped out. In our last lecture, we talked a little bit about drawdown and cones of depression. We'll talk about that maybe a little more, or I'll have a slide or two on that for another lecture for our international friends. But this aquifer is pretty much at kind of ambient pressure. There's no pressure that compresses it, and it flows downstream or downhill. It might emerge here where there are springs, wetlands. It's going to connect to a stream, and the stream, which is of course the surface water, is moving down much faster than an aquifer to the sea, but both will end up in the sea at some point. But we have other aquifers, and that's what I find so interesting. And this is really important when it comes to remediation, to cleaning up aquifers. And that is the confined aquifers. These move down, and because they can't go up, they're squeezed, if you will, by two aquitards, which means layers of rock that are so impermeable that the water can't move into them. This whole thing is pressurized. In fact, you can imagine it's got a lot of pressure because the water in this what they call recharge zone, where it's raining and adding a lot of water to the aquifer. Those are the mountains. You got that way uphill. So you got all the influence of gravity. We call that hydraulic head, driving and pressurizing this system. Well, if the system were completely porous, you didn't have all these rocks sort of pushing back, it would, move fast. But it can't move fast. It's got a lot of pressure, hold back pressure by the rocks, and so it's a very pressurized system. And that's why if somebody comes along, and it has to be a deep well, they'll spend money drilling that deep, they'll drill all the way down to that, and the water will come out, sometimes fast, under an artesian well. We call it an artesian well because it's generating the flow just by virtue of being there where it is and tapping the pressure of this system that drives it up. And sometimes, I guess it's a little complicated to show in this slide, and I'll just allow you to use your imagination of how it works. But sometimes with, pretty cracked, if you had like a steep hill here and some cracked soil, you get artesian springs. And artesian springs are ones that are dramatic, and you may have seen them. There's often little tourist spots where the water just seems to be roaring out of the ground. You and I went to Soda Springs once, and a big crowd of people go there because it's really cool seeing the water come out of the ground so fast. And then the last aquifer that I'll talk about today, again we're going to get into more detail on this, is a perched aquifer, where you have some kind of I call it a clay lens, an impermeable, a small impermeable aquitard, which means it's a very dense area, rock that's so dense that it's impermeable. That would be like rock with a lot of clay. I'm going to talk more about soil particles in another lecture. These would tend to be sand, and this would tend to be a clay, because clay is impermeable and sand is porous. It's got more particles in it, so it's going to resist the water going down, which means you're going to have a water table on top of that, but it's a small water table as opposed to kind of what might be called the grander or more extensive water table in just one area. If you were to put a well in here for some, high demand like agriculture or power plants, which I talked about, they're very thirsty for water. They use it to cool their equipment. Then they're going to run out of water pretty fast. So they're probably going to put their well deeper. In fact, this whole zone we would call, a zone of intake, a screened area where the well has little holes in it so that it can take in the water. Or they could drill all the way down here, and then of course they save the expense of pumping the water out. So here is what's happening underground. And here I'll leave you to study. These slides will be posted. This lecture will be posted that you can see it again. It's just all the ways that humans, if you will, insult the subsurface. You can't see the pollution. Sometimes we say the pollution is insidious because the guy that might be pumping water and using it for personal consumption may be so far removed from the source of pollution that they just don't make the connection. My water has a really funny smell, and yet I live way out in the country. Why is that happening? Well, 20 miles away, there's a gas station, for instance, where the water is being spilled. I should say the petrol is being spilled and going into the aquifer. Or one of the very insidious sources of pollution is when tanks full of fuel are placed underground. They put them underground for the sake of avoiding fire danger, because they're very safe against fire. But then when these guys leak, you may not even know it. You just say, man, it seems like I put 100 gallons in there and I only got 60 gallons out. Well, they're losing the rest to leakage, and that leakage isn't just going away. There's no way for it to go. It's going into this aquifer and being transported, maybe slowly, but to the point where 3 weeks after it starts leaking, the guy who lives down river or down gradient, we say in the case of aquifers, they're going to notice, man, it seems like our water smells like gas. We've had that problem out where we went, and I took you guys to the wetlands. We took some movies, the wetlands that the students put in, and the people in the neighborhood down, if you remember, we could see them down there about 300 meters on the other side of the fence off campus. Those guys complained that their water smelled like sewage and tasted bad, and that's all coming from our sewage water, from our septic tanks actually, failing and carrying that sewage water into their neighborhood. That's one of the ways that our university is not a good neighbor yet and wants to improve its environmental performance, which is why our work is so important here. So mines, landfills, dump areas such as Sharon Yandev and I work on are all sources of this type of pollution, subsurface pollution that goes into mostly these unconfined aquifers with an unpressurized water table. But sometimes, particularly, in the United States, I'm sure this happens in parts of Nigeria where it's still legal. It's illegal in the United States, is when an oil industry has a bunch of pollution, they say, man, out of sight, out of mind. Let's just take that well that we used to use to pull the oil out, it's exhausted now, and dump all our hazardous waste in there. And then if this thing leaks here, it can go right into the aquifer. And even if it doesn't leak, the discharge goes down here, and it might be hundreds of miles away. Of course, it would take years to get there. Then an artesian well will bring it to the surface. Okay, I have about 5 more minutes, and that's pretty good. This is a drawing from the research that Sharon Yandev and I are working on. We surely hope to publish it in a journal such as the Journal of Environmental Management or Environmental Quality. And we see a pile of surface waste. We don't really bury our waste here in Nigeria. So we have piles of waste sitting on the surface. They're a nuisance, a significant health threat to humans around it, which is why we're studying it. And far and away the most significant health threat that's life-shortening in our community is the burning of waste. All the plastics. It's just really bad burning those plastics, and the chemicals that come off are serious respiratory insults, and people breathe them. At times we know, main way you know that this is happening is because of the way the air smells. The air has this sour, very unpleasant smell. That's burning waste, particularly the plastic, including those containers from our cafeteria, those takeaway containers. You can see them over there at the dump, 100 meters away from the cafeteria, and they burn to get rid of nuisances like, the waste food will attract flies and rats and so forth, but they're creating this. Now, pertinent to water, particularly to to our research, Sharon's and mine, is we know that another pathway is surface runoff. This is really non-point source pollution, that the rain that goes through is picking up these pollutants and carrying it. And then insidiously, underneath the piles, we have this leachate. It rains, lots and lots this time of year. It mobilizes the pollution to where you have this toxic soup, things that are easily dissolved. Gravity is driving it down. We're going to see a lot more examples of this in the lecture on oil field contamination next week, or it's on Thursday. Get a little more detail. And then we get to the water table, and then this here, it shows that the water table is going this direction. You can see the pictures of the waste there. And here you can see that the pollution, it doesn't show too well, but you can see the pollution sits probably mostly on top of the aquifer, because a lot of leachates, especially if they're hydrocarbons, are lighter than water. You know how you drop oil on water and it's on the top, even makes rainbows? So those are lighter than water, so they sit right on top of the water table. And then some will, and they often don't dissolve in water. Oil and water don't mix. But some of it may dissolve in water and move along the sort of, not the very top of the water table, but near the top, in the saturated zone. This would be moving through the unsaturated zone, that portion that's above the blue line, and the portion below the blue line would be in the top of the saturated zone. And one thing that this slide doesn't show is that some of the waste will actually, as pictures in the way, just go straight down. Those would be heavier, completely non-soluble toxins. And there's not a lot here. Maybe some pesticides are that way. I spent a lot of my career cleaning up facilities in the United States, like big computer plants, and they clean, they're called degreasing agents, and they clean the chips right after they've made them of any grease before they put them in computers. And those solvents like trichloroethane and trichloroethylene, they're heavy, they go right down. The most interesting project just about I ever worked on was a military base with these huge bombers that are part of our Cold War conflict with Soviet Union, and they sprayed their wings with this obnoxious chemical almost all the time when it was cold. It's called a de-icing agent. Those of us who fly around the United States, sometimes right before you, or UK, right before you take off, it's kind of weird looking in the snow. This guy comes out in this suit, and he's in this kind of lifty thing, I think it's called a man lift, spraying this weird stuff on the wings, and that's to keep the wings from icing up, because the plane will get too heavy and crash. And those drill down and go really deep, and they're terrible pollutants because they go all the way to the aquitard, and then they start moving, and so they're, you know, even more insidious. Okay, the last slide I'm going to end on. There's actually two more. I'll show another time when I'm focusing on desertification, but this is to leave you with and look at, you know, kind of at your leisure, I'll be sure and show it again, is the influence of desertification on the water cycle. No, not really desertification, all of global